In the last 3 lectures, we built something most circuit courses skip completely. A mathematical reason for why a nonlinear device like a MOSFET can act as a linear amplifier. We linearized it. We built a small signal model for first principles using Taylor series, right? But here's the questions we never actually answered. What makes a two-port network an amplifier in the first place? Not what makes a MOSFET an amplifier. What makes any device, any black box qualify as one? That's what today is about. By the end of this video, you will have a mathematical checklist, 4 conditions that any device has to satisfy to be usable as an amplifier. And I swear, once you have the checklist, it won't matter if the device in front of you is a MOSFET, a BJT, a FinFET, a DGFET, okay, a CFET, or something that doesn't even exist yet. Okay, if it passes the checklist, you can build with it. Okay. So let's get into it. So this is lecture 4 of the series, the final model of amplifier using BMR. BMR standing for bare minimum requirement. And I am Sabir Bhuya, analog and mixed signal IC designer, founder of Analog Brain. So quick recap before we move forward, because everything today builds directly on this. Okay. So in lecture 2, we ran into what I call the active passive paradox. So every electrical component in this universe dissipates powers, right? That's just physics. That's passivity. Uh, but we use device like the MOSFET as active device. So the resolution was they are active in incremental domain, not in absolute terms, in the small signal sense. In lecture 1, and in lecture 1, we hit the linearity nonlinearity paradox. To get power amplification, you fundamentally need nonlinearity. But to get faithful amplification, amplification without distortion, without generating harmonics, you need linearity. And the moment you bring a nonlinear element like a diode or MOSFET, all your favorite circuit theorems, superpositions, Thevenin, Norton, stop applying, right? And we saw that. Uh, lecture 3 was the resolution to that paradox. Keep the nonlinear element but locally linearize it around an operating point. We build that linearization framework using a Taylor series expansion, and that what come the other end was the small signal model. So today we take that framework and push it one level further. Okay, we extend the incremental linearization to a full two-port network. Okay, we use that extended framework to build the final mathematical model of an amplifier. From that model, we derive the exact constraints our device parameters must satisfy to qualify as an amplifier. Only then do we go pick a device and check whether it satisfies its small signal model or not. Okay, so notice the order here. This is the whole philosophy of this course. We don't start with here's a MOSFET. Let's see what it can do. But we start with here's an amplifier mathematically requires, and only afterwards do we go shopping for a device that delivers it. Okay, it can be a MOSFET, okay, or it can be a FinFET. It can be your sub 20 nanometer FinFET, or your CMOS 55 nanometer. Your it can be your DGFET, right? Or it can be a GAAFET. Okay, so let's see a two-port network setup. So this is a two-port network. Okay, our black box two-port nonlinear. So this is A prime, our port 1. This is current of port 1, I1. This is B prime. This is current of port 2, I2. Okay, so our assumption, so this is function I1 F1 VA prime VB prime VDD. I2 is a different function of this three thing F2, and I3 is a different function of this three thing. The assumption is the VDD is not changing and it is not dirty, but the thing is in real circuit the VDD can also vary. Okay, so you need LDO also. So this is not our topic for now. We are assuming that the VDD is perfect. Okay, the rail is not changing, and our point of interest is input port and output port. Okay, so this is I1 F1 VA prime VB prime. This is I2 F2 VA prime VB prime. The thing is, according to the point of interest, we are focusing on this 2 and remove VDD as it is not changing. Okay, so note that those two equation denoting only bias operating condition. So you can so this I1 is actually IG, your gate current. Okay, this is a function of VAA prime, VBB prime. We are generalizing it. This VAA prime is nothing but your VGS. This VBB prime is nothing but your VDS. If I talk about a MOSFET, okay, this I2 is nothing but your IDS. This VAA prime is nothing but your VGS. But this is VGSQ, your quotient VGS. Means it's your it's only your bias. Okay, VB prime it's your VDS. So note that those two equation only denoting only bias operating condition, and we have to apply a small signal voltage riding on that bias. So assume that we already applied the small signal and we got current small signal swing, and the port 1 and port 2 current will now change. Okay, so let's see. So this is I1 plus del I1. So this del I1 is nothing but the current due to the signal swing. Okay, and this is this del VAA prime, this is VGS, your small VGS, del VBB prime, your small VDS. Okay, so the change in current is equal to the current of the signal swing, and the change in the voltage is equal to the voltage of the signal swing. Okay, so I replace the del VAA prime with small VAA prime, and this del I1 as a small I1. So this is small IG, this is small I, capital small I, small d. Okay, small ID. So this is small VGS, this is small VDS. Okay, nice. So let's apply Taylor series for the first equation, I1 plus del I1, F1 VA prime plus VA prime. So the thing is, this is a multivariable Taylor function. Okay, a multivariable Taylor series. So uh, we'll apply for multivariable, we'll apply like a single variable Taylor series. Okay, it is absolutely simple. This F1 VA prime VB prime, this is what this I1. Okay, this is because of this quotient operating point operating condition, and this will be cancelled out. So this is the variable VA prime. Okay, so dou F1 dou VA prime means we are differentiating with respect to the port 1 voltage. Okay, and we are differentiating around the operating point VA prime VB prime. This is the operating point, your VGSQ and VDSQ. Okay, so this is and this is for the second port, and this is the second differentiation, dou square F1 dou VA square, and this is VA square by 2 factorial. This is that will be 2 factorial, and another time will be VA prime divided by 3 factorial dou cube F1 dou VA 5 cube, and around that operating point. So that's exactly simple thing. Okay, now here we apply Taylor series expansion, and we'll omit the hot. So what is what here? What is hot means? Hot means higher order terms. So what can be omit only and only if the signal is small enough. So here I1 is VAA prime dou F1 dou VAA prime. Okay, I omit the higher order terms. Okay, now the thing is, we can also do this for I2 same way. Okay, so now two clean up steps here. First, naming, we rename the small signal voltage. Okay, we represent slope as y parameter, and I also choose a proper naming for the port voltages and operating voltages. Then we will arrange those linear simultaneous equation in matrix. Okay, so let VAA prime our V1, small V1. AA prime means V1, VB prime V2. This is V1Q, V2Q means quotient point of port 1, quotient point of port 2, and this F1 is nothing but this F2 and I2. So Y11 is dou I1 by dou V1, V1Q, V2Q. This is nothing but this thing. Okay, so this is actually Y11 dou I1. I replace this VAA prime. Okay, VBB prime. I replace those things. Okay, that's the thing. So dou I1 dou V1, V1Q, V2Q, dou I1 dou V2. So Y11, Y12, Y21, Y22. So the thing is, when we write, we will write y11, then y12 here, y21 here, y22 here. So these two things will be replaced. Okay, uh, so now the thing is, so here's the final this is the final y parameters, and here is the final clean linearized framework. I1 is equal to, I replace those term y11 v1, y12 v2, y21 v1, y22 v2. Okay, so this is I1 I2 and this is the matrix form. And now this is the actual circuit. This is the actual two port circuit. So one important physical reading of each parameter, take y1 as the example. So uh, the thing is, it is the ratio of the incremental change in I1 to V1, while V2 is held constant, which in small signal terms just means V2 is equal to 0. Each y parameter is a partial derivative. A slope on an IV curve measured with the other port's small signal voltage shorted to 0. Keep that other port shorted intuition. It's going to matter a lot in a few minutes. This four element Y matrix is now a fully general linear model of any two port network around an operating point. Linear, non-linear, doesn't matter what's inside the box. The non-linearity has been absorbed into the four numbers. This is Y11, Y12, Y21, Y22 evaluated at the bias point. Okay, so now a few important framing points before we start optimizing our goal. Okay, so this is I1, this is I2, and this is I1, Y11, V1, Y12, V2. So we are about to find out the constant of Y parameters to be an amplifier. Okay, so this is the two port, and we want to this two port to be an amplifier. Okay, so let's apply KCL in port 1. Okay, not KCL, it's your Ohm's law. Okay, V in minus V1 by RS. Okay, and uh, apply KVL in port 2. So eventually you will get those two equation, right? And from this you will get GSV in Y11 plus GSV1. Some mathematical manipulation, just common this out. 1 by RS is actually GS. Okay, so and 1 by RL is equal to GL. So take this thing to the left and common out V2, then Y22 plus GL plus B2. Y22, this will be plus GL. Okay, sorry for the mistake, this will be plus GL, Y22 plus GL times V2. Okay, so now this is, yes, this is plus GL. Now so this is the matrix. We'll apply Kramer's rules and find out the V2. So Y2n, Y21 GS, V in, Y11 plus GS, Y22 plus GLs, Y12, Y21. So you all know the Kramer's rules. And the thing is, V2 is V out. So V out by V in is nothing but this thing, Y21 GS, Y11 plus GS, Y22 plus GL, Y12, Y21. Okay. So solve the 2 by 2 linear system in matrix form. eh? Okay, use Kramer rule. So now our goal is to maximize V out by V in for amplification. To maximize, okay, and maximize the power delivered to RL. So it is not necessary that the incremental Y parameter should always be positive. It is partial derivative of a nonlinear function. It can be negative as well, but for most of our device we'll find it positive. So we are setting constraints ourselves to that that we'll use positive value. If we can choose the value of y11, y12, y21, y22 such that the denominator becomes 0, then the gain will infinite. Okay, so if we can choose the value of y11, y12, y21 to such that the denominator becomes 0, uh, then the gain will infinite. Okay, but there is a problem. Infinite gain means there is output available without the presence of input. Okay, so borderline instability, which means oscillation. So here's the harder constraint, and it's an engineering one, not a math one. We have to build this amplifier so it works robust, robustly. Okay, sorry, under conditions we don't get to control. So so we don't know what source impedance GS or load impedance GL the customer is going to connect. We don't know whether our Y parameters will hold constant or drift with temperature, right? Or shift across a process corner, what called PVT variation. So the blunt truth is the amplifier is going to be built out of real silicon, real devices, real device characteristics, okay, that do changes with PVT. And the bottom line for a product you intend to sell, that you can't take that risk. An amplifier that only works at one specific GS, one specific GL, one specific temperature is not a product. It's a lab demo. So instead of relying on a delicate cancellation in the denominator, we need to look at the circuit level structure of the Y matrix and find constraints that are robust by construction, not by coincidence. Okay. So to do that, we redraw the Y parameter matrix as an actual circuit. Okay, so this is the actual circuit. So each ports gets an admittance 1 by Y11 and 1 by Y22. Just look at this one, I1 Y11 V1 Y12 V2. So if I say this Y11 is related to this port V1, that means it's a resistance. Okay, 1 by Y1 V by R, and this Y12 it relates with the another port voltage, not this port. Okay, so this can't be a resistance. This is this must be a voltage control current source. Okay, so similar is this. Okay, so uh, the thing is each ports gets an admittance 1 by Y11 and 1 by Y22, and there are two voltage control current source. Okay, Y21 V1 at port 2 and control by V1, and Y12 V2 at port 1 and control by V2. So this is just a standard two port Y parameter equivalent circuit drawn straight from the equations. Okay, so having the circuit picture in front of us is what lets the next several slides reason physically port by port about what each parameters is actually doing. Okay, so let's see let's see so start at the input port. Okay, so what do we want there? We want our amplifier to accept all the input signal voltage no matter what impedance the source present. So we want our amplifier to eat all the, okay, all the signals. So in other words, we want to maximize V1 regardless of GS looking at the circuit. The only way to guarantee that is for the input port's own admittance to vanish. So Y11 is equal to 0. 0 input impedance means infinite input impedance. Nothing is loading down the source. So the full Vin shows up at V1. So that's the thing. So we are also fixing our intended signal flow directions. So we apply the input port, okay, at 1, and we take output from port 2. Forward, right, left to right, left to right. That choice is what makes next two constraint make sense. Okay. Uh, so now the thing is, now look at Y12 V2, the current source at the input port. Okay, this one, the current source at the input port, that's controlled by the output voltage, right? So physically, this term is stealing some of the output signal and feeding it backward into the input. So that reverse transmission or back transmission, we actually don't want that. An amplifier whose output leaks back and corrupts its own input is at best unpredictable and at most another path toward instability. So the constraint is Y12 is equal to 0. No back transmission, which raises the natural next questions. If Y12 is the backward path that we are killing, which parameter is the forward path? The one actually responsible for transferring signal from port 1 to port 2. So that's Y21. And this is genuinely the core of the amplifier. Here's the physical story. So Vin is applied at port 1, which produces V1. So port 2 gets excited because the VCCS, voltage control current source, at the output, okay, is sensing the voltage V1, and in response injecting a current Y21 V1 into the output node, okay, in the opposite direction. that injected current develops V2 across the load. Okay, so Y21 is literally the mechanism doing the amplifying. It converts an input voltage into an input current. That conversion ratio is a transconductance. So unlike Y11, Y12, which we want to kill, we want Y21 has to be largest possible ideally. So Y21 tends to infinite and Y12 should be 0. So last one, the output port impedance, right, Y22. So we want the entire current that Y21 generates, Y21 V1 generates, entire current flow through only the load resistance. Okay, the entire current. But uh, this Y22, when Y21 generates Y21 V1 to flow into the RL and develop the full output voltage there, right? But the output port's own admittance represented as Y122 is a parallel path that steals some of the current away from the load. So the constraint Y22 is 0. So 0 admittance at the output port means it offers no alternative path for current. Everything Y21 V1 produces is forced through RL. Admittance 0. Here literally means we are not giving the current permission to flow through that internal resistance. It has nowhere to go but the load. Okay. So let's put all four together. So y11 is equal to what? Y11 should be is equal to 0. Okay. Maximize V1. Guarantee it will so guarantee high input impedance, no loading on the source. And y12 is equal to 0. Guarantee no back transmission from output to input. Okay. Y21 it's infinite. We want as large as possible. Infinite is not possible, so we not don't write that y21 is equal to infinite. Infinite is a concept, not a number. So y21 tends to infinite, so it maximizes forward transmission. This is where the gain and speed come from. And y22 is equal to 0. Basically this y21 is nothing but your gm for the MOSFET. Okay, so we are talking about any device, so we are generalizing it, not on we are talking about not only for MOSFET. But if you think with a MOSFET, then this Y21 is your GM. If you think with a MOSFET, then this Y22 is nothing but your GDS. Okay, so 1 by Y22 will be your RDS. So Y22 is equal to 0, guarantees no current is diverted at the output. All of it flows into the load. Okay, no parallel connection, no CLM effect. So if you have channel length modulation in your MOSFET, you won't have y22 is equal to 0. Okay, so this is the whole answer to the question. I opened the video with any device regardless of its internal physics that can be operated such that it satisfies this four condition, qualify as an amplifier. Okay, so now the thing is, when we drop these four conditions into the y parameter circuit, almost the whole circuit disappears, and 1 by y11, 1 by y22 are gone. Okay, so infinite impedance, no branch, 1 by y22 is gone for the same reason, and all that's left is a single voltage control current source y21 v1 sitting between port 2's terminal. That's it, and that is the entire bare minimum amplifier, a single dependent current source. Okay, so in matrix form is nothing but 0 0 infinite 0. So basically this is our amplifier, the mathematical amplifier. Okay, that's the thing. I like that matrix a lot. Okay, I used to write a lot. So the thing is, if you take the full gain expression from slide 10 and substitute in y110, y120, y220, and the denominator collapses to just gs and gl, and you are left with the strikingly some simple result. V out by v in is minus y21 rl. So if you talk about a MOSFET, this is nothing but your common source amplifier with a resistive load. Okay, but the thing is your gain is depending on RL, but this is voltage control current source. We are talking about V out by V in, which is a voltage amplifier. So we'll see later which drive and which load, which block can drive which load, and also the other thing. But for now, this is the amplifier. Okay, this is our mathematical model of our amplifier. So now see, here's really important nuance before we go to pick a device. It's not a requirement that the slopes exactly zero, okay, or exactly infinite across the entire operating range of the device. We only need them to hold in some region of the device IV characteristics. The region we choose to bias it in, okay. So the thing is, suppose this is for a MOSFET, this I1 is also 0. So let's see this two. Suppose this is I2, this is I2, so this is V2. So this is nothing but ID VDS. So we want this type of things. Just remember your ID VDS curve. You have like this some curve and like this your flat region, your saturation region. Okay. So we want this region. Okay. So it is not necessary. Okay. That the slope has to be 0 or infinite everywhere. So now the thing is, let's choose our device as MOSFET. Okay, the MOSFET, here's the beautiful part is that for an ideal MOSFET, the gate current is 0. Okay, so I1 is equal to Ig is equal to 0. Since I1 is identically 0 regardless of V1 or V2, both of its partial derivatives vanish automatically. Y11 Y12 come from free. Okay, so just from the device physics of an insulated gate, no biasing trick required, it's built in. Okay, so that leaves two conditions still to satisfy. Each one maps to a specific recognizable IV curve of the MOSFET. So Y21, we need this large, ideally near vertical, comes from the slope of the ID versus VGS curve. Okay, so it's nearly impossible to have a slope like 90-degree. So ID versus VGS curve, that's our transconductance. Y21 is actually our GM, and Y22 we need this near 0, ideally flat. So comes from the slope of ID versus VDS curve. That's your output conductance 1 over RO. So the entire job of biasing a MOSFET as an amplifier uh, reduces to find the region of ID versus VGS curve where the slope is steep, and the region of the ID versus VDS curve where the slope is flat, and operate there. Okay, so we haven't said the word saturation region yet on purpose, right? Notice you can already see exactly what this is going, purely from the math, purely from the scratch. Okay, before we ever invoke device physics vocabulary, so we are using mathematics. So actual the workflow in order is, so plot the device's IV characteristics first. Okay, then check whether those four constants are satisfied somewhere on that graph or not. So this is your two-port device MOSFET as an two-port device. It can be BJT, it can be MOSFET, it can be DGFET, FinFET, GAAFET, CFET, anything. Okay, and here's the generalization that makes the whole lecture worth the effort. So this checklist is not specific to the MOSFET. If you hand me any device, completely different carrier transport, completely different device physics, and it can satisfy the same four constraints somewhere on its curve, I can build an amplifier out of it. The underlying silicon doesn't matter anymore. BJT, MOSFET, double gate FET, FinFET, gate all around FET, CFET, doesn't matter, same checklist every time. So this is the reality of this course, of the entire course. So let me say it plainly. We just derived a complete working definition of amplifier using nothing but mathematics, Taylor series, partial derivatives, KCL, without touching device level physics even once. Math is the language of the universe. You don't need to drop down the device physics to design at the circuit level. That is a very concrete consequence. So this course is PDK independent. Everything we build from first principles using BMR, not tied to any specific process design kit. So when you eventually run into a double gate FET at 55 nanometer, or a FinFET below 22 nanometer, or a gate all around FET on a 2 nanometer node, anything, absolutely anything, any device that may not be in volume production yet, you own starting from zero, you will already know exactly what to check for because you derive the checklist yourself. So to summarize where we landed, an amplifier stripped down to its mathematical essence is a device that gives you zero input impedance, zero reverse transmission, zero output impedance, and as much forward transconductance as you can get. Phone numbers. Okay, the phone numbers. And that's the entire spec. In the next lecture, we are going to pick up exactly where slide 20 left off. Take the MOSFET, IDVGS, IDVDS curve, locate the region where this constant actually hold, and apply the Taylor series to tool from lecture 3, extract the real small signal model, GMRO, and everything that follows from them. So in this kind of first principles approach is useful to you, hit subscribe. Lecture 5 is coming next. I will see you there. Okay, goodbye.